Hi everyone, my name is Martin Feick and I'm a PhD student at Saarland University and a member of the FKI in Germany. This work was part of my master thesis research that I conducted at the University College London last year. But first and foremost, I would like to introduce our team, consisting of myself, Scott Bateman, Anthony Tang, Andre Miede and Nikolai Marquardt. And if there's one thing that I really want you to take from this talk, then it's TanGi proxies lead to higher object embodiment, which eases virtual object exploration and manipulation. And now we are going to unpack this. But let's start by looking at this video that we obviously recorded in our lab. And it also might exaggerate a little bit, but here Roxana has a hard time interacting with the virtual bunny because it's very challenging and cumbersome to form precise manipulations with virtual objects. And this is due to the existing limitations of conventional controllers and freehand interaction techniques. So by giving the bunny a physical manifestation, for example by 3D printing it, it becomes much easier to interact and manipulate it in the environment. But of course, giving virtual objects a tangible form is not a new idea and has been explored in the past. Most notably is the fundamental work by Hinckley et al., where they use tangible elements to manipulate content on a simple 2D display, and the theory of tangible bits, demoing many examples on a tabletop. Recently, we have seen approaches utilizing everyday objects that already exist in the environment as proxies for augmented reality, or using a toolkit composed of Lego bricks with embedded hardware to build functional proxy objects for virtual reality. Our work extends previous work by introducing new types of manipulations, which we will introduce later. It also expands on systems like virtual bricks by allowing the creation of tangible proxies, not underlying shape and size limitations of Lego bricks. To do so, we propose a set of primitive 3D printed shapes that people can use to rapidly prototype a variety of handheld-sized objects. To provide this initial set of primitives, we run an informative lab study. However, the central idea is that each user would have their own customized set of shapes dedicated to the needs of this user. The primitives are highly customizable and more versatile, since there are fewer limits to the shapes that can be 3D printed, and of course reusable due to the specific Velcro pattern that you can see on the right-hand side. And here is a video from one of our studies, where a participant built a Stanford bunny using our composable shape primitives. Obviously, this is only an approximation, but on average it took them 2.5 minutes to build an object instead of 25 hours to fully 3D print it. Following this assembly step, they could use it as a physical proxy in virtual reality. However, real-world physical objects have a vast complexity. For example, parts of objects can be rotated, translated, stretched, bent, and so on. And this is only a subset of possible object interactions, but these are the ones we focus on in this work. So going back to the bunny, rotating his head does not work with a stiff 3D print or with an assembled object. Therefore, we designed and implemented the manipulators using commonly available fabrication methods and low-cost off-the-shelf hardware components. Manipulators are self-contained and provide inside-out tracking. The manipulators enable users to build objects with parts that can be rotated, translated and stretched, as well as bent. Together with the composable shape primitives, they built the TanGi toolkit, allowing people to quickly build proxy objects, including movable parts. And the toolkit is also open source. To demonstrate TanGi's capabilities, we built different use cases and applications. For example, now the bunny can rotate its head using TanGi's rotation manipulator. Or building a crossbow in VR by using the stretching manipulator. And a catapult with the help of a bending manipulator. Finally, we demonstrate the use of 2 manipulators simultaneously in order to control a virtual robotic arm, providing 8 degrees of freedom. We conducted 2 user studies to further evaluate the TanGi toolkit and to understand how different levels of object embodiment affect object exploration and manipulation. In the first study, we focused on how increased levels of object embodiment affect object exploration in virtual reality. We compared 4 conditions, starting with a virtual bunny offering no physical embodiment, all the way up to a high-fidelity 3D print. We recruited 16 participants. In the first part, participants were instructed to build a bunny using a given set of primitive shapes. You can see the 16 somewhat different bunnies on the right side, which they also used in the second part of the experiment. And subjects reported that it was easy to assemble the object. In part 2, our study task consists of 2 different interactions. First, referring to a specific detail on the object, the sphere, and positioning and orienting the object so that it matches another one. This task was modeled around a common interaction in VR when exploring objects from different angles. We found that with increased level of object embodiment, participants performed better across all measurements, and physical operations aligned more closely with people's expectations. For example, by looking at the questionnaire responses, participants found embodied objects easier to learn and easier to use. However, to the question, I could point at the object accurately, responses in the TanGi condition were quite mixed. And this is due to the fact that participants built their own proxy that they used in the study. Some proxies were, for example, bigger than the virtual objects, and thus participants could simply not reach the location. Vice versa, some participants decided to not include ears in their replica, and therefore did not receive haptic feedback when touching the virtual ears, as you can see here. So, when giving people the ability to build their own proxies for virtual reality, for example with the help of a toolkit, their experiences will ultimately differ. In contrast, with a high-fidelity print, such instances did not occur. As a result, participants favored this condition. However, compared to the freehand and controller condition, subjects stated that TanGi proxies allowed them to better understand the size and dimension of the object, because it was much closer to what they were actually holding in the virtual world. In the second study, we looked at object manipulations, comparing freehand, controller, and TanGi. We recruited 12 participants. We looked at bending, rotating, and stretching an object. In the second experiment, we used the same matching task as in study 1. We found that participants both preferred and performed much better using TanGi, if we look at the task completion times, for example. TanGi was faster with significantly lower completion times. Or when looking at the questionnaire responses, TanGi received better ratings across different conditions. For example, it was easier to learn and easier to use. Further, participants reported that there was no additional layer between them and the virtual object in the TanGi condition due to the direct mapping between the virtual and the physical object. Moreover, they could simply apply the movement they learned because it was much closer to the real world. However, for more details on the studies, I would like to refer to the paper. And to conclude here, we have shown that the conceptual design and implementation of TanGi allows to build proxies leading to higher object embodiment, which is an effective way to ease object exploration and manipulation in virtual reality. Thank you very much.